Alright, so we're going to do another optimization problem. Found this on the internet. I'm giving credit to the gentleman up in the upper right. We have a piece of cardboard that is 14 inches by 10 inches, and we're going to cut out the corners, as shown below, and you notice I covered that up for a second, and fold up the sides to form a box. Show, determine the height of the box that'll give maximum volume. Now listen, often this is a real world problem. You cut the squares out of the corners, and that's what this picture shows, is that you're going to cut out a little square h by h. And what they did is they dimensioned the piece then, based on it being 10 by 14. And in this picture, they dimensioned everything out. And they also then showed how the box looked once it was folded up. I think this is a good starter problem, but I think in the long term, you can find this problem as worded. We have a piece of cardboard that is 10 by 14, and we're going to cut squares out of the corners and fold up the sides to form a box. Determine the height of the box. And you would have to be able to build these two pictures. But we know we have these two pictures. We know we want to make the volume a maximum. So it is an optimization problem. It has nothing to do with time. So we're going to have to maximize the volume. And I see here, I can write the volume equation immediately. Volume equals h times 14 minus 2h times 10 minus 2h. And it's a great equation because it's all one variable. So if we multiply our binomials here and then distribute the h, we can simplify this volume equation. And again, just pause me and work ahead if you want to try to solve this to this. And now we can say, well, we know that h has a domain probably from greater than 0 to less than 10 or less than 5 because it has to be there. So we have a domain on this based on the side, the short side of the box here. So we're going to take the derivative of the equation and we're going to set it equal to 0. So with that said, I get b prime equal to 140 minus 96h plus 12h squared. And again, I'll probably write it this way. And we're going to set b prime equal to 0. So this is a case where we either got to use quadratic formula or complete the square. Perhaps I'll use the quadratic formula, and we know that if we have ax squared plus bx plus c equals 0, that x is equal to negative b plus or minus a discriminant, b squared minus 4ac all over 2a. So in this case, I have a is 12, b is negative 96, c is 140. And I know there's a program for this in your TI calculator. I can write this as 96 plus or minus the square root of 96 squared minus 4 times 12 times 140 all over 24, because that's 2a, 2 times 12. And if I do the math here, I can get this down to 2 solutions. I can get this, again, using my calculator, to 4 decimal places, again, preparation for the AP test. I'm going to get 2 values. Now, what we have to catch is what we stated back up here, is that h has a domain. It cannot be any smaller than 0, can't be 0 or smaller, but it also can't be greater than 5. So we find that x has to be 1.9183 inches. So that is the height of the box that gives the maximum volume. Now, if we want to check this, we can do the first derivative test on either side of this. We can plug in, say, v prime of 1, and find that if we put in v prime of 1, it's greater than 0. And if we say put in v prime of 2, we can find that this is less than 0. So the first derivative, it goes from positive to negative. Thus, by the first derivative rule, since it goes from positive to negative, 1.9183 is a maximum. Again, optimization problems, they take practice. Keep going.